Good afternoon, everyone. Welcome to the last plenary session of EAS 2023. I'm Sara Lucatello. I'm one of the vice presidents of the Society, and today I have the pleasure and the honor to chair the closing session with Staszek Zola, one of the co-chairs of the Scientific Organizing Committee. I will be presenting the prizes and the closing ceremony, while Staszek will be chairing the talks by Gillian, Wright, and Christiane Helling. It is my honor and privilege to introduce the winner of the 2023 Jocelyn Burnell Inspiration Medal, Mariano Mendez of Captain Astronomical Institute in the Netherlands. Many of you will know Mariano for his excellent work on high-energy astrophysics, but today he's being honored for his contribution to society through astronomy. Mariano developed a program of education on space science for the benefits of the large community of young scientists in developing countries. The citation reads, "The 2023 Jocelyn Burnell Inspiration Medal is awarded to Professor Mariano Mendez for his work over decades to set up a program of education in space science in developing countries around the world." This is the medal that we're presenting to Mariano. Big round of applause. And the certificate. Indeed. Thank you. Yeah, I will hold it for him. I'll keep it safe while he gives his talk. Hands-on science in developing countries, a 20-year endeavor still going strong. Take it away, Mariano.
Thank you very much. You can keep the medal to make sure that I give my talk properly and give it to me only after that. I don't know how, do I start this or I have to wait for someone to start my PowerPoint? I can speak without the PowerPoint, but yes. While it comes. Oh, there it is. Okay, then I go. Okay, so thank you very much for this honor from the European Astronomical Society for the work I've been doing these past years. I want to tell you a little bit what is this initiative, the COSPAR Capacity Initiative and the IU Hands-on Workshops Initiative, so the two. I have been chair for the COSPAR Initiative for a few years, 8 years, and before that vice chair. After 8 years in COSPAR, you have to move out, so I moved out. And then the IU thought, oh, we can do something similar, and so they asked me to do that. I hope this is how it works. No? Oh, yes. So the idea, which was not mine, I just got invited to join in 2001, that's when we started, was to organize workshops in developing countries at the time to teach young scientists how to use data from X-ray observatories. That's how it started. It was an idea of someone called Peter Wilmore. Some of you may know him, may have known him. He died 2 years ago. He was retired and he thought, I can do something. I have contacts in COSPAR and COSPAR can put some money. So we started in 2001 and I was invited as a lecturer of that workshop, the first workshop. And then from that point on, we continued doing every 2 years or so another workshop. And I was again invited. And after a few, I got in part of the organization, and after a few years he retired completely. I took over, and that's what I'm going to talk about. So the workshops are highly practical, so the students are not necessarily students, they can be young staff members. They go and do some practical work on real data from real space missions, or now from the IU, from ground-based observatories as well. And sorry, but I'm not sure how this, oh, there it is. Why was this necessary? Well, we live in a world, now it's 2023, this started in 2001. Of course, there was internet at the time, it's not that old, but it was not the same as now, and even now, it's difficult for a scientist in a developing country to know how to access data that are there, are publicly available, but how do you get to use them? How do you get to download them? Which data do you have to download? Which software do you need to use to analyze those data? What can you get out of that? I come from a developing country. I come from Argentina originally, although now I'm in the Netherlands. And I got at some point an opportunity to do science in a developed country, and I thought it's a good idea to try to help others like me to do the same. There are reasons why you don't have access to those things. Okay, now internet is faster, so maybe you have now access to internet, but still the awareness in the developing countries is very low. So are those data really public? Are they available? Not only astronomy, here we are in an astronomical society, but also Earth observations, atmospheric observations, ionospheric observations. If there is no tradition in those developing countries, especially on space science, so you don't have satellites, you don't have people working on instruments that fly on satellites, you don't have launchers, so you don't have access to those things. And those data could be useful not just for science, also for science, but also for society. So that was the purpose of this thing, and the buttons are a bit small. And so, as I said, Peter Wilmore in 2001 introduced this idea, and then eventually I took over and I expanded it into areas that were not served before. And so we did things on crystallography in space, ionospheric science, space weather, things that now come to mind. I have a list later. And we look at the data that were available to organize these workshops. And so at that time for COSPAR, it was Initiative for Space Science. Later I took over for the IU, and we did it for Earth observations as well, but only astronomy. So this map, what it shows, I have to look at the map while I speak, so I have to be careful with the microphone. This shows the places where we organized workshops so far, since 2001. All the red squares are places where we organize a workshop with COSPAR. The green ones are where we organize a workshop with the IAU. Mind you that COSPAR exists since 2001, the IAU initiative since 2021. So we only had one round of workshops from the IAU, and the second round is coming soon. But look at where they are distributed. The very dark countries are developed countries where these needs are not so big. So Western Europe, the US, these are places where people can get access to those things. The very light color countries are countries where the science developments are very far behind. And even if we organize a workshop there, our impact would not be that big. Something more basic is needed to start with. So we'll focus on countries in between, in the gray area, the colors more into the gray area, so where there is science, but it's not at the highest developed part of the world. And we repeated workshops in some places on different topics, but the same area of the world, and the nature is always regional. Try to make the attendance coming from countries near the one that hosts the workshop. Here is a big list that you don't have to read, but it contains all the workshops until, I think, 2021. And the numbers on the last column is a program that I will not talk about, that we organize also called the fellowship program, by which we give a short-time fellowship for 4 to 8 weeks to participants of these workshops. To show you a little bit of pictures how these things happen, people are sitting behind the computers. As you see there, these are old pictures because all these are desktops. Nowadays, most of the students bring their own laptops, even from developing countries. We offer local laptops or desktops for those who cannot get them, but most of them prefer to bring their own. Peter Wilmore is the person on the top left. And we went all over the world, and there are also social activities. Well, here is more laboratory work shown, classes shown, etc. And there is a lot of social activities to try to engage the relation between lectures and students. The one in the middle is me singing. I'm a terribly bad singer, but it was funny. I was a clown, and everyone laughed at me, and that breaks the ice. It's very important to make a community among the students and the lecturers. Eventually, these lecturers will write letters of recommendation for these students when they go for PhD, postdoc positions, or will simply take them as postdocs themselves. Some of the lecturers, I like to do magic. I'm an aficionado magician, and I do magic for the students. But we have lecturers who play the piano, lecturers who sing, who dance, who do juggling, even someone who had interest in theater, recitation. So you see there 3 students sitting on the, I don't know how to point to that, but it doesn't matter. There. They were reading a novel called Copenhagen, which is the story, imagine a conversation between Niels Bohr and Heisenberg. And we even had once Heisenberg, a black person playing Heisenberg. It was very funny. So you need good astronomers, good scientists, but you also need good people to hold these things. Here is a list of the workshops, the ideas, the topics, and the areas where we had these workshops with COSPAR, and I wrote about 2,000 students. These are, as I said, not necessarily students, but sometimes young staff members, and about 200 lecturers. It's usually 1 lecture per 3 students, but because many workshops were repeated and the same lectures came again, the number of lecturers that attended these workshops is a bit less than that. And for the IU, we have so far organized 3 of those. There are 2 or 3 more coming. Now we are ranking them. We will finish selecting them in a week or so. And so far, we have trained about 100 students, and we have about 30 lectures. So what are the things that makes these workshops a success? There are 3 things. The lecturers, and the lecturers. And I saw some lecturers here. Conrad, I see you there, and I saw Jose Cericharo. I don't know if someone else who was a lecturer in this workshop is sitting in the audience. Can you raise your hand if I see you? Conrad, you're there, right? Yes, I saw you. Well, these people deserve a similar prize because they come to these workshops for 2 weeks. They don't get any payment for doing that. They only get their travel expenses paid and their lodging expenses and food, but they don't get any salary. And they spend 2 weeks of their own time, sometimes holiday time, teaching to these students at about 60 hours a day. This is very demanding. I've heard from people who were lecturers who were not expecting that and told me this was the most demanding thing I ever did. And then they came again later, surprisingly. So I want to thank those lecturers as well. They are anonymous in big parts, because without these people, we cannot do these things. And these people are there for their own reasons. I get to that in a moment, but they are not there for money. So that brings me to the last part of my presentation, and I think I'm doing quite well. I was going to go shorter than the half an hour I have. The first part of my last part is people want to know what happened with the students that go to these workshops. What do they become? Okay, I can tell you a success story of a student that went to become some head of a department or professor or working from the Indian Space Research Organization. All those things happen. We have examples of those. But let me tell you the story of R.E., which is a real name, but because of these new laws about privacy, I might not be able to mention his name, so I don't. If you deduce who he is or she is, let's be neutral, it's your decision. R got his bachelor's at the age of 27 and his PhD at the age of 40 at this university in Nigeria, which is about 600 kilometers away from Lagos. He got his PhD at around 2004. At that time, we organized a COSPAR workshop in South Africa, and he was selected and participated there. Once he finished, he remained in touch with one of the lecturers of the workshop, and they were doing something as a follow-up of the project that they did during that workshop. His university did not have computers to access the internet in 2004-05, I'm talking. They only had dial-up internet access. So when he, R, wanted to contact his colleague, he had to go to an internet cafe and write emails. His colleague At some point, had a laptop, a desktop that was so old that he replaced, and he put it in a packet and sent it to Nigeria to this guy, so he would have a computer. Then R wrote a proposal from what he learned to observe with Chandra, a white dwarf system. And he got the time. It was the first ever Nigerian astronomer to put a proposal for Chandra. That's what Chandra told us. And it only happened because he attended this workshop. He won the proposal, and in the US, when you win a proposal and you have a US-based COI, you get money, so that money was used to bring him to the US to work with his colleague there. And they published the paper, and that was quite good. He returned back to Nigeria, and there, over the years, became a senior lecturer, and he supervised about 25 undergraduate students and half a dozen of graduate PhD students. And this information is old. I'm still friends with him on Facebook, but I'm not looking at those things very often. But it gives you an idea that he has made a mark in those students. Even if he's not a fantastic scientist. He's a very good scientist, but not, at the top of the notch, getting all these grants and publishing in all these Nature papers. But he was very tenacious. And he got the opportunity and went back to Nigeria to put some seeds and let others grow and get what they get. I forgot to do something in the middle of my talk that I normally do when I do my lectures and my talks, is just to play a little game with the audience. Do you hear me if I speak here? No? Oh, I need my hands, but okay, let me see. Okay, do you hear me? Can you play with me? I want you, also you, to put your hands like this. This is to show you the sort of atmosphere we build in this workshop. So you put your hands like this, you turn them like that, you cross them like this, and now you put your index fingers forward and your thumb down. The chairperson is doing it fantastic. Copy her, she's doing it great. She's the best. Is the president of EAS here? I always like to say, Mr. President, oh, you're doing things right. I always like to say, Mr. President, you're wrong. But in this case, you're right. Okay, now that you have the hands like this, if you practice good enough, if you are very flexible, you should be able to do this. No? You couldn't? Okay, so what you saw is what happens in our workshops besides astronomy. Honestly, we teach astronomy, but all these things break the ice. I will not explain how I did it. I'm very flexible. Thank you very much for this. But these kind of things that we do help break the ice with the students. And as I told you, we have people who play the piano, we sing, we dance, theater, juggling, I don't know. That helps a lot. So now I come to the real end of my talk, is to see what is things that motivate us. So I saw a couple of lectures here at the EAS, and I wonder what motivates them to do what they do. Why do they go to teach for 2 weeks, 60 hours a day for no money? Even using up their holidays sometimes. And of course, why do we who organize this do this? There was a psychologist, Abraham Maslow, who in 1943, this is true, 1943 tried to figure out what motivates people by looking at all papers published at the time, and he made this list that if you look, it's a sort of pyramid, you can look it up on Wikipedia, and you go down, what are the things that motivate people to do things? Physical needs, hunger, thirst, security, safety. He organized them in this order, saying going from low necessities to higher up necessities. To belong in somewhere, to have a love, family, affection, maybe be competent, gain approval, become independent, know, understand, aesthetic art, beauty, realize your potential, self-fulfillment, and to the top is help others realize their potential. I like to think of myself, I'm a bit arrogant, I'm sorry for that I'm at the top of that. I like that. I like to do that. I like to help others realize their potential. And these lecturers I only see Conrad now, but there are many more. They did the same. They got no salary. I'm sorry that I say it so much, so many times, but these people deserve prizes like I'm receiving today. It's incredible, their commitment. And they do it because something moves them to do it. Now you should think, why are you here today? Why did you wake up this morning and come to this place? Why did you fly to Krakow? What do you want to achieve? Is somewhere in that list what you want to achieve. So there was this philosopher who said, dwarves standing on the shoulders of giants, and I feel standing on the shoulders of Jocelyn Bell, which is someone very well known. I'm not standing on her shoulders because she's very short. I met her a couple of times. And when I was a student, I always admired her as someone who very unfairly did not receive what she deserved. You know, this is the story of Goliath and David and all these stories that you as a student think, oh, this could happen to me. I met her, and she's a very nice person and very inspirational. So I'm very happy to be standing figuratively on her shoulders. And I hope that I'm a giant in a different way, because if you look at me, I'm tall. I'm not at her standards of giant, but I would like to have someone else on my shoulder standing there. He's sitting over there. Is my son who came to support me. He's not looking like that anymore. This is a few years ago. He's much older. But I do also things to try to motivate him. Thank you very much for the prize, and thank you very much for the time. That was it.
Thanks, Mariano, for this inspirational talk. You deserve a big thanks from all of us for what you do. Is there any question for Mariano? If you have a question, please raise your hand very high so I can see you. And I would appreciate if you said your name before starting your question, name and affiliation, so we recognize you. And also the people from Connecting could know who you are.
Hi, I'm Tek Adhikari. I'm from Nepal, so maybe not developing but underdeveloped country. So I had this privilege to do my PhD in Poland at the Nicolaus Copernicus Astronomical Center, which was also somehow related to my, first exposure to one of those black hole accretion conference that was being organized in Kathmandu by most of the European institutes. And I really appreciate what, Professor, you are doing for the development of astronomy and space science in countries like my country. So I just wanted to say you thank you so much for this kind of initiatives that can motivate us, like people like me, who were, not having this access of data or any scientific opportunities. So my question is, do you plan to continue these kind of activities in future in our part of the world, like in also in South Asia?
Yes, thank you for the first part and answering directly your question. I'm still part of the COSPAR initiative, not chairing the panel, but chairing the fellowship part. And we are still receiving proposals and organizing workshops with COSPAR at about a rate of 3 per year. Not only in astronomy, just mind you, it's also space science to look at the Earth or magnetosphere or the sun or whatever. It's not just astronomy. With the IU, we organized already 3, and we are planning, we issued a call for proposals, and we received 7 proposals to organize 2, hopefully 3, in the period 23-24. Great. We did not receive anyone from Nepal. We received proposals from Thailand. And we will continue, at least, I've been asked by the EU to do it for 5 years, so I hope that for those 5 years we get funds. I hope we will. We need to thank many institutions for their funding, you know, NASA, ESA, JAXA, ISRO, I cannot name them all, foundations like the Moore Foundation, I don't know. We get money to all and we keep doing them as far as there is interest in the community. And the first round for the IU, we received 11 proposals. The second round, we received 7. It's an oversubscription of a factor of 2 now, 3 before. We try to do as many as we can. If you have any idea of organizing a workshop about a specific instrument that you think is worth learning, has to be in a developing country, not in Europe, please come forward. We help you write the proposals. The proposals in the end compete, but we try to help you as much as you can, we can, to make the proposals competitive. So if you come with a proposal on Nepal, we would be happy to organize that. We put certain amount of money, order of 35,000 euros, and we need some funds locally because that's not enough. We have to pay all the costs of the stay of all the participants, no registration fee, all the travel cost of all the lecturers, hopefully some help to some of the students, we'll see.
Thank you so much. I look forward for a collaboration to organize this kind of activities in our region. Thanks.
There's another question.
There is one here down, I don't know, there was another one, I cannot see one. I'm not going to explain how I did the trick with the hands, so don't ask that.
First of all, congratulations to this marvelous prize. I was wondering, you speak about the COSPA fellowships. Are they directly linked to these workshops, or are they open to everyone who wishes to apply to them?
Yes, these fellowships are open only to people who participated of these workshops. And the idea is to offer them a chance to interact more with one of the lecturers of the workshop. If they study the project and the lecturer and this person think that they can pursue it further and hopefully write a paper, we can provide some money, the host might provide some money, sometimes your own institute, the student's institution also provides. So we try to find a financial solution to bring the student for 6 weeks to this other laboratory, but it's only for people who participated of these workshops.
The question from the back.
Hi, my name is Marilia Carlos. I'm currently working in Uppsala University, but I'm from Brazil, a developing country. So I'd like to thank you and congratulations on the award. And my question is, now I'm a postdoc, and if I want to be a lecturer on this program, how would I would apply?
Yes. The way it works is the local organizer, so people propose. Once you propose, you are selected maybe. If you're selected, you will come up with a team of lecturers. You can ask us to provide you with some suggestions. In the end, it's your responsibility. Of course, we share part of the task. And so in the end, is if you are connected to the people who propose, the chances is that you will be selected. We don't issue a call for potential lectures. We don't do it that way. And of course, depends on what is the topic. I don't know, last year we organized one in X-ray astronomy in South Africa, one on VLTI in Chile, and we are now organizing the third one of that period in Turkey and Iran on radio astronomy. And so depending on what your specialty is and how your contacts are with the people who organize, you might be contacted by them. If you want to contact us and offer yourself to be lecturer of some of the workshops, if those are selected, it's fine, and we can propose your name, but in the end, it's a matter of the organizers to decide.
Okay, great. Thank you.
Thank you.
We're going to wrap up now because it's time, and also because Mariano has a flight to catch.
Yes.
Let's thank him again for his wonderful work. Thank you so much.
Thank you again, and sorry I cannot stay.
And then I pass the baton to Staszek for the next 2 talks.
Good afternoon, everyone. My name is Staszek Zola. I work for the Jagiellonian University, which is based here in Krakow, and it's the oldest university in Poland and one of the oldest in Europe. I got several questions, so I'd like to tell this about my university. I'll be sharing the next two talks, which will be given by two distinguished speakers. And first of the speakers will be Professor Gillian Wright, who is a director, who is a director at the UK Astronomy Technology Centre in Edinburgh, also European PI for the James Webb Space Telescope MIRI instrument, and a visiting professor of the Institute for Astronomy, University of Edinburgh. Out of numerous awards and honors, I will mention just two. In 2006, Queen Elizabeth II made Professor Wright a member of the Most Excellent Order of the British Empire for her services to science. And the recent one, she awarded this year, she became the first UK winner of the Caroline Herschel Medal. Her focus is in infrared region of the electromagnetic spectrum, and instrument she was engaged in work with. This is UK infrared telescope on Mauna Kea, and then ESO Herschel mission, and the most recent one, James Webb telescope. And the talk will be on this one, so we'll hear about James Webb telescope. Professor Gillian, the stage is yours.
Okay, so thank you everybody for the invitation to speak. And how do I make this go forward? Okay. So wow, what a year it has been for the James Webb Space Telescope. It is really, really hard, for me at least, to actually believe it's been only a year, because there's just been so much new science, and these absolutely fabulous, wonderful instruments are just amazing. The images are incredible. I think we've heard a lot of science talks at this meeting. So what I would like to do with this plenary talk is just take a little bit of a step back and talk a bit about how we got here, about the mission, and then just some pieces of science that are, for me, personal highlights and that I think are very exciting. So, it's an amazing observatory. We should remind ourselves that this is the biggest telescope that's ever been launched into space, and that to do it, it had to be deployable with a segmented primary mirror, and there had been very few telescopes built on the ground with segmented mirrors. It's an infrared telescope, so the whole observatory is cooled to cryogenic temperatures, and the instruments are optimized for the infrared. I think launching on Christmas Day in the end was kind of quite an amazing thing to do, and that was in December 2021. It's a year since the first images were released because there was 6 months of commissioning, but the launch was so perfect that we now think we've got a 20-year or longer science mission. So we're here at the EAS, so just thinking about all the things that Europe contributed to JWST through the European Space Agency, the launcher, the NIRSPEC instrument, and also the MIRI instrument, which was built not only with ESA funding, but through additional contributions of the member states in 10 European countries. And also now ESA are part of the mission operations at STSCI. And it's easy to talk about this in terms of, oh, Europe did this bit, and even within the MIRI team, the different institutes involved, we all had different responsibilities. But I think the key point here is that when you do this, you're a part of creating the mission in a much broader way, and it's an amazing thing to do. So although ESA was responsible for the Ariane 5 provision, the whole mission would never have worked if the integration between what the observatory was capable of and how it was built and the European launch vehicle hadn't been looked after in a lot of detail by both NASA and ESA. So the mission team becomes integrated, and I think the people involved in the mission from Europe had an enormous influence on all sorts of things that are not so easy to capture just by saying, oh, we did this bit and they did that bit. It was a very broad role in the mission that ESA took on, and a lot of European companies and European scientists have made a massive contribution to making this instrument come into existence. So just thinking about the clock, so Europe, I think ESA signed up around 2000 formally as a mission partner. Construction began in 2004. It's been a very long process. The mirrors were getting made even before the launch vehicle had been selected, the instruments all coming together. We delivered the first instrument, MIRI, from Europe. The optical system for MIRI was delivered to Goddard in 2012. That was a really important milestone on the critical path for the construction of the whole observatory. Once the telescope was completed and integrated with the instruments, there was a long period of testing and testing again, leading up to that 2021 launch. So we shouldn't forget what an amazing series of engineering firsts this mission absolutely has been. Passive cooling of such a huge structure in space with an enormous sunshade that had to be deployed all the way to 40 Kelvin. There are no cryogens on the mission at all for the first time on an infrared mission. Deploying the telescope in space, the segmented mirror, how you line all those mirrors up to make sharp images. That had been done, for example, for the Keck telescope on Mauna Kea. It took a long, long time. To do it in space, where you do not have the capability to go and tweak things, is a massive engineering step forward. So I know the MIRI is cooled to 7 Kelvin, so it brought its own challenges and additional challenges to the mission to be able to do that, one of which was the development of a very low power vibration-free cooler by JPL in the United States. Without that, and I can tell you that Mary spent years having conversations around, would our cooler actually cool the observatory? Everybody that's been involved in building this mission has many, many things to say about all the different things that happened along the way, all the problems that had to be solved, because there were just so many engineering firsts in it. And I think the instruments fall into that as well. Really sophisticated instruments that were designed to work well with an 8-meter class telescope. And we know from the ground-based observatories that those instruments become far more sophisticated and complicated on the ESO 8-meter telescopes than we were used to seeing on 1-meter and 4-meter class telescopes. So being able to do that in space, I think that was an engineering first as well. Specially developed detectors for the mission that have proven to be absolutely superb. So I think it's very easy now to almost take the science for granted. It's been so fabulous over the last year, but this engineering is what's made it happen, and I think it's an enormous credit to all of the agencies involved. There are, mentioning the instruments, there are 4 instruments and they underpin 17 different ways of observing, which is a massive, powerful suite. They also all complement each other, and I think we're seeing that in the science, the multi-wavelength science that does not come from just a near-infrared instrument, or it does not come from just MIRI, the mid-infrared instrument, but it's across the infrared wave bands, and the different techniques that they enable and the different ways that they can take observations all play together in an integrated and very powerful suite on this observatory. So after around April time, after launching on Christmas Day, NASA released these images of the Magellanic Clouds. I think this was the real evidence that not only did the observatory work, but the images were all beautifully sharp and in focus. And you can also see the beginnings of how they complement each other. So one of my favorite, where's the laser? One of my favorite things to point out is the images have fields of view next to each other on the sky. So this is the large Magellanic Clouds. You can see in the near-infrared instrument here, you can see a dust lane. You can actually trace that all the way across to the Murray field of view and see the dust in emission. And I think this was the first real observational view of how the near and the mid-infrared wavelengths complement each other on the mission. And of course, it is an absolutely massive change in capability. So this is comparing Murray image in the Magellanic Clouds with the previous best available mid-infrared images, and you can see how much the physical size of the telescope and the spatial resolution it provides, what a massive difference that is making. So people made this observatory, and yet 20,000 scientists and engineers from all over the world contributed and took part in making it happening. That teamwork of the entire mission and the attention to detail is what's giving us the amazing science now. So I think we shouldn't forget that there was an enormous effort from a lot of people over 25 years to build this mission. So moving on to some science and some exciting things. One of them is, I think, exoplanet characterization, and the way the observatory is an absolutely exquisite tool for not for finding exoplanets, but for actually characterizing what are their atmospheres, what are they made of, understanding how they formed better. So this was the first ever detection of carbon dioxide in an exoplanet atmosphere, but of course it was very quickly followed up in the same exoplanet by a lot of other molecules, and it's really the spectroscopy of exoplanets is underpinned by the enormous pointing stability of that great big observatory and the stability of the detectors to make these faint transits. So something that I think is a pointer to future science from this is that if we really zoom in on the NIRSPEC spectrum down here, this little feature, the sulfur dioxide, was not predicted in the existing models of exoplanet atmospheres. It really was new and something quite unexpected. And the explanation for it is that there's a need to include photochemistry in the exoplanet atmosphere into the modeling of the atmosphere. So you've got water being split into H plus OH radicals that can then form the silicon dioxide through a long chemical chain. So this is some of the more recent work now. You can see that there's a very good fit. A number of different atmospheric models. You can see the quality of the fit here to the NIRSPEC data. And also, it makes a very clear prediction for what the spectrum should look like at Murray wavelengths, which has now been observed. And I think this is just highlighting how much for exoplanets, having this very, very broad wavelength range is going to be a real key to getting to the bottom of what the chemistry in these atmospheres actually is. So, moving on to rocky exoplanets, we've had the measurements in the TRAPPIST system. So these planets are tidally locked. So they have a hot side and a cold side because one side is always facing towards their parent star. In the case of TRAPPIST 1b, the temperature measurement and the high temperature that's been measured using photometry at infrared wavelengths indicates that this planet absolutely does not have an atmosphere. It's a bare rocky planet. If it had an atmosphere, then just as on Earth, the atmosphere would be distributing the warmth around the planet, and that would give you, on average, a lower temperature. TRAPPIST 1c has now also had its temperature measured. It's consistent with there being no carbon dioxide in the atmosphere. And there's a concerted effort now in cycle 2 observations with JWST to really understand a lot of this detail about the TRAPPIST system with a lot more observations scheduled. So I think there's a lot more news to come here. And we shouldn't forget, of course, the importance of being able to do direct imaging. So the first slide, one of the first results from the early release science program was this one. And of course, once you can do direct imaging, then you get very tight constraints on the planet's bolometric luminosity and the radius, because you're measuring them directly rather than inferring them, and that leads to robust mass estimates for the planet. So this is important, but it's now being followed up with this system in HR 8799, in which the star in this system's in here, so we've got direct detections of floor planets. So this is the first direct image of a planetary system rather than an individual exoplanet. And you can see G up here is a background galaxy. Its colors are consistent with it being a star-forming galaxy at about a redshift of 1. This is a result that's in preparation for publication now. But I think the power of this direct imaging, we've got some early results that indicate this is going to be a very powerful technique with JWST in the future. So I'm going to move on to the absolutely opposite scale of things now and talk about dust formation. This is this Wolf-Rayet star, it's a binary. It was known to have a dust shell, but that's all that was known, right? And so there'd been some modeling of how that dust shell was there, the dust formation. Now you can see there are over 17 dust rings have been measured. There's a detailed model being published in Nature. You can see how well it reproduces the process and the dust creation, and we know that these are PAHs that are being formed here from the spectroscopy. So I think this is an example of how, even for individual sources, the level of detail that's being provided in the JWST data is really leading to new understandings of systems and how things work. So moving now to galaxies and the distant universe. So I think there's been loads of new results from the deep images. This one is the JADES image. I think it's absolutely beautiful, but the SEERS and the PRIMER deep surveys have also been finding the unexpected and producing equally amazing images. There are more than 700 candidate galaxies at redshifts bigger than 8 in this image. So we are now moving into a regime where high redshift galaxies and galaxies at the epoch of reionization, which were rare individual things that could be studied one at a time, and there was very few of them. So you're making big extrapolations when you try and understand the early universe from them. Now there can be proper statistical studies, samples of galaxies. And of course, the 700 candidate galaxies are identified on the basis of photometric redshifts. But what's really important is that with NIRSPEC, so now rather than NIRCam and MIRI working together on our NIRSPEC and MIRI on the exoplanets, now we're looking at how NIRSPEC, as a multi-object spectrograph, can really follow up these faint high redshift sources that are being discovered in the deep imaging. So these are now the faintest and the most distant galaxies measured. You can see that they're stretching, and it's beautiful data. There are clear measurements of the Lyman break in these galaxies. There is no doubt about the redshift of the things that we're seeing. They're not red because they happen to be red galaxies. They're red because they're very, very distant in the earliest epochs of the universe and galaxy evolution. So I think this is significant in its own right, but it indicates the future and how amazing it's going to be. And within that, within those galaxies, another big discovery that has been recent and in the news is also the discovery of populations of small and distant black holes. So we're talking about black holes that are redshifts beyond 4 or 5, and their masses are much smaller than we would typically see in quasars. This spectrum, you can see it's got lots of little bumps and wiggles. Every single one of those is real. That's not noise in that spectrum. If we zoom in on a logarithmic scale, now you can see where the noise is, and now you can see all the broad lines, not only hydrogen lines, but ionized species as well, which means that from this, actually, you can measure the black hole mass in these sources. So this is absolutely something that couldn't be done before JWST, and this is the latest result on GNZ11 is one of the most distant galaxies known. It was known about before JWST and known to be very luminous. There's now clear evidence that this is a black hole, but also if you look at what's interesting is about how black holes form and evolve in the universe. So if this is even accreting well under the Eddington limit, you can see how this black hole now in the high redshift universe can evolve into the things that we see around redshifts 6 and 7. So I think, again, this is the beginnings of what's going to be a very fruitful field of understanding galaxy evolution in ways that we couldn't do before because we couldn't measure the galaxies without the sensitivity of JWST. And while we're discussing quasars, this is now, at these redshifts, MIRI is a little bit different because you're looking at rest frame near infrared light. So, but you can see here a comparison, a fit. So this is a quasar at a redshift of 7, and the data would indicate that this very distant quasar is almost exactly the same as what we see in our nearby neighborhood. So this is a black hole that has evolved into something that we see in our nearby neighborhood less than 800 million years after the Big Bang. So really in the early universe. So I think there's a lot of study in how black holes form and evolve that is being opened up here. And of course, rest frame, being able to see the rest frame near infrared is also important when what you're looking at is dusty star-forming galaxies. And we know this in our nearby galaxies, that where the old stellar population is not necessarily the same as where the star formation is happening, or the most recent star formation. And this is an absolutely perfect example. Here's the Hubble image showing you where the young stars are. But in a near-infrared image with JWST, you can actually see that there's a large mature stellar disk. It actually looks like a normal galaxy rather than this kind of thing. This one is complicated, but again, you can see there's an old stellar population associated with both where the hot young stars are and where the dust is indicated by ALMA. So we've got two star-forming galaxies here interacting. So that is, I think, only the beginning. I think the exquisite stability of the observatory and the wide wavelength coverage is massively underpinning the exoplanet science, and from that to the fact that the telescope really does have the low background and the superb sensitivity that was predicted for it, it's really providing transformational capabilities, and I honestly don't think it's an exaggeration to say that a new era of scientific discovery has really begun. So we're late in the afternoon of a busy conference, so I thought we should just finish by enjoying a movie that I can stop any time, but Isa put this together in celebration of the first year of images from JWST, and I think it's really nice. It shows you a whole pile of images and science that I haven't talked about. And thank you for listening. Let's just enjoy. And if people have questions, I think.
Thank you very much. We still have some time, so please enjoy the movie for 1 minute, and then with
Actually,
Gillian.
it's 3 minutes.
3 minutes. Then Gillian will take questions.
This is one of my favorites. Does everybody have a favorite image? Pretty much. Yeah.
Are there any questions? Anyone? Can't see at the back. Maybe there is one. No questions. Everyone enjoyed the film. Thank you very much.
The movie was nice, yes.
Good music with sky art. Thank you very much again. Let's thank
you,
the
everybody.
speaker again. And there is another talk. I invite here Professor Christiane Helling, who serves as a director of the Space Research Institute at the Austrian Academy of Sciences. She is also a professor in space sciences at Graz University of Technology, as well as the honorary professor of physics and astronomy at the University of St. Andrews, UK. Before I tell about her a little bit about her research, I can't resist to read this. The required foundation is a good education. You don't have to be an overachiever, but you need the courage to persevere, the courage to admit mistakes, and a passion for science. Good networking is important in all career phases. In any case, dream big, but take realistic steps. This I cited for our young colleagues, and this is what Professor Helling said in an interview some time ago. I guess this was in German, but I found an English translation. The final word, research which Professor Helling does is aimed at deciphering of chemical composition of atmospheres of exoplanets, and we'll hear about exoplanets in our galaxy.
Thank you so much for this very sweet and very kind introduction. It's always a revelation if you realize that people actually read what you have said at some point. So, my name is Christiane Helling, and my task is today to talk about the planets in our galaxy. And I came to, probably like as many of you, to the realization that, of course, every planet must be in a galaxy. And by now I start my talks with this. Do I have a pointer? I do. With this little sketch, because we all know we live on Earth, right? And Earth is part of a planetary system, but our planetary system is part of a stellar vicinity. And so we go bigger and bigger. Our solar system, our stellar vicinity is also part of a galactic vicinity at some point, and at some point we are also part of a cosmic web. And therefore, I think we do well to think about exoplanetary science as a science that actually encapsulates many research areas, including even galaxy evolution at some point. Let's get started. I would like to set the stage by reminding us that we, as of a couple of days ago, know about the presence of 5,417 planets outside our solar system, which we call extrasolar planets. For those of which we know their masses and their radius, which you see here in this plot, we can make a bit of a demographics. So here are planetary masses, planetary orbits, and you see they are kind of spread out over this plot, but just kind of. Down here we would expect our favorite rocky planets, but we also have many planets that are far bigger, far more massive, than Jupiter. Here is the one Jupiter line. So, and those we are calling giant gas planets. And you also see that some of them are residing very far away from their host star. Now we can add a bit of complexity by looking at the effective temperature of their host star, and this is color-coded here. But the interesting aspect comes now if we look at the radius of these planets, and we see that there is a certain correlation with planets orbiting hot host stars compared to those and their radius. You see down here the rocky corner isn't too much affected, but if we go up into the gas giant corner, that you see clearly that we have several very, very large gas giants which orbit rather hot host stars. So here we have another clear indication that the host star matters not only for the chemistry but also for the evolution and potential mass loss eventually. Now, the biggest question that we have as researchers is humanity's place in the universe. So our questions are then, what is out there? Or maybe even who is out there? And in order to explore this question in a more fundamental way, our task is really to look into the reasons for the diversity, for this huge diversity of extrasolar planets that we know of, for why our Earth, and with that our solar system, is so unique and so much tuned to life as we know it, and then deriving from this our responsibility for our home planet Earth. So what I'm saying here is basically that we as astronomers have, based on the knowledge and based on the gifts that we have to carry also our piece of responsibility for our own Earth. So, of course, every observation we do only inside the solar system. This is a bit heartbreaking, because only inside the solar system we can really go and do in situ measurements, which is fantastic. And we have seen the JUICE launch, and we see these beautiful pictures and measurements coming back. But of course, we have a whole suite of other space instruments, and I'm showing here a slide from the European space missions, which they title as Cosmic Observatories. This is plotted as function of wavelengths. Here we have the active missions, and here we have the future missions. And if you are now looking a little bit what is in there for extrasolar planets, and I'm sure many of you have spotted your favorite space mission already, but here I'm just thinking about exoplanets. And you see there is quite a fleet of space missions that help us not only to find the extrasolar planets, which we only find in the intermediate neighborhood of our sun, but which we expect to be, of course, present throughout the entire galaxy, since at least each of the stars has at least one extrasolar planet, so we expect a lot of them to be out there. But there are also more space missions to come. I would like to dwell a little longer on that thought, or on the effort that actually ESA is putting in to help us to achieve our scientific potential. And here is a table that Markus has made available, and I would like to invite you to look at the first two columns. First of all, you see a list of ESA-led space missions, and then you also see the launch date. And now there are a couple of quality indicators. You can pick your favorite one. They all tell, of course, a story, but for now, let us move to the last column of this table and have a peek. Because what we all found very important. Does someone want to join me here? What we all found very astounding is the comparison between Planck and Cheops. So if you look at this, Planck has been launched in 2009, and we all know it's a cosmology mission, and Planck is the mission with the highest impact factor in that table. If you now go down to Cheops is an exoplanet mission, the first mission really used to characterize extrasolar planets, which has been launched 10 years later. And Cheops is the second, Cheops is the mission with the second highest impact factor in this table. And this, of course, tells us that cosmology and extrasolar sciences are really major drivers of our scientific communities, for good reasons. Right. Thank you, Gillian, for laying out the way to James Webb. I don't need to say anything more about this. I would now like to lead over to a couple of thoughts on characterizing extrasolar planets. So, of course, and one of the working horse will be James JWST, but we of course have other space missions out there, and we as a community also use ground-based observations for doing so. Now, if you think about characterizing an astrophysical object, you have to be quite precise what you're actually talking about, and with planets there is no difference. So there's one very simple way of characterizing your extrasolar planet. You determine its mass and its radius, and then you can put it in this plot of it, which I have squashed up there in the corner, because I'm more interested in the derived properties, like, for example, the gravity of the object. And then we do some magic and we have some more observations and find an estimate, a value for the global temperature, in order to be able to see, is this a colder, is this a hotter planet? So with the mass and with the radius, I get my y-axis of the plot that I'm interested in, and it's the gravity here in CGS units, and here we have a global temperature. And what we did here, we just placed all the JWST targets in this plot and overlaid a couple of objects that we were particularly interested in, for example, HD 189733b, for those who have ever heard this phone number. Why are we doing this? Well, because we want to characterize these planets, and the first step in doing so is categorize them. So can we identify characteristics which are typical for some groups of these planets? And of course, I have chosen this plot exactly for making that point. So you see that the gravitational acceleration is kind of similar, somewhere between 10 to the 3 and 10 to the 4 centimeters per square centimeters per square second. And here we have our temperature scale. On the very right-hand side, at the higher temperature end, at temperatures of larger than 2000 Kelvin, we have a class or a category that we are calling ultra-hot Jupiters. A little bit in the middle of this plot, we have those which we are calling hot Jupiters, and they are hot because they are not cold, which means they are warmer than about 1000 Kelvin. So they are sitting between 1 and 2000 Kelvin. And then we are already going into what we would call a little colder environment, where we have the so-called warm Saturns. Here we have in yellow the heads 6b. And then as we move further towards lower temperatures, we enter the Neptune-like or the Neptunian extrasolar planets. And here is one example given. Now, having certain categories is of course nice, and in particular if you want to develop a certain physical understanding for these objects. But this can't be all, right? So now we have the observational properties on one hand side, but in order to really understand what's going on, we need to utilize so-called virtual laboratories. So we need to develop theories, we need to develop consistent models in order to make predictions and then compare this to the observations as we get it, for example, from JWST. What I'm going to do, I will show you a temperature map in order to form your perception of what kind of climate and weather these planets may have. And I base this on three-dimensional simulations. So we will have a three-dimensional atmosphere, and I will slice through the equatorial plane, open it up, so that we see the temperature map inward into the atmosphere, but also a two-dimensional view. And here it is. So here you have your temperature map for a warm Saturn. Here you have the temperature map for a hot Jupiter, and here we have it for the ultra-hot Jupiter. On your left-hand side, it's always the night side. On the right-hand side, it's always the day side. What I would like you to see is that for the warm Saturn, everything looks relatively, maybe even boring, so relatively homogeneous, spherical symmetry, you could say. The further we move towards the hotter part of this plot, the larger the day-night differences become. You see here, for example, for this WASP 39b model, that the night side becomes considerably different than the day side, and this is really being driven home by the ultra-hot Jupiters, where we have a temperature difference between the day and the night side of about 2,500 Kelvin. This is, of course, immense, and this also has implications for our observational expectations. For example, would we have an atomic gas on the day side and a molecular gas on the night side? And this means we have geometrically very differently extended atmospheres. So the day side would be much more compact than the night would be much more compact the night side would be much more compact than the day side. So as this has such strong implications for the chemistry, we now need to think about clouds, because what we really want to do is we want to analyze those beautiful spectra that Gillian just has shown us for JWST. The question is, what is it actually what we see? And it turns out what we always see is only the tip of the iceberg. Here I'm showing you now a cloud map, and we see that a warm Saturn would be covered in clouds. It means we can't look into the atmosphere. We only see the carpet of clouds that hinders us actually to explore what the atmospheric characteristics are, or even what the evolutionary state of the planet may be. For hot Jupiter, we see that the day side has a more extended cloud than the night side, and everything becomes completely diverse, meaning we have very, very different physical and chemical processes acting on these ultra-hot Jupiters, which makes these ultra-hot Jupiters quite unique laboratories to study a wide range of physical and chemical processes. So here on the right hand, on the day side, we would even think about ionization processes, where we really talk about phase transitions on the night side. So there's a lot of fantastic fundamental physics to be explored in these extrasolar planets. Now, but what is it what we actually can observe? And I am taking half a minute or so to walk you through this slide, because I think as simple as the methodology is, as ingenious the idea actually is. So what we have here is a so-called transit spectrum. A transit is when the planet moves in front of a star, and the flux of the star, or the flux of the system, decreases. Now, with JWST, we can do this entire exercise for a large range of wavelengths, as Gillian has just shown us. And here I'm just showing I'm showing one example. So here are the transits for all these wavelengths, and what is now done. The depth of this flux drop is measured and plotted as function of the wavelengths here. So here we have the transit depths, here we have the wavelengths, and it's exactly the same plot that Gillian showed. What the researchers did now here is they tried to figure out which gas phase or which atmospheric species actually contribute to this frequency-dependent wavelength flux drops during this transit event. So, and we see there is water. There's a clear detection of water. We have CO2, also H2S, so a sulfur binding molecule CH4. Which is of interest for a couple of reasons, CO2, but also the already mentioned SO2, and then there is an indication for clouds. But the interesting part is here actually what we are not seeing. And this is, for example, the clouds. We are not having any information about the magnetic fields. From our solar system experience, we know there must, or hopefully is, a magnetic field to shelter, to protect the atmospheres of these planets. So, and maybe going back to the SO2 feature, yes, this is a new development, but this also tells us that we have to really combine our theoretical studies with the observational studies. So one can't really live without the other. Okay, so, but there is more into this, and now I would like to go a little bit into prospects of what else can be done. Because extrasolar planets are certainly not spherical symmetric spheres, but they are asymmetric. And here I'm now showing you exactly what we would see if such a planet moves in front of a star, which parts of the atmosphere are visible. So we are having now a terminator temperature map. So if the planet moves in front of the star, this is the temperature you would see. And we see here a difference between between the evening and the morning terminator of about 500 Kelvin. So the question is now, can we use our instrumental capabilities to actually tease out more about the physics and chemistry of such asymmetry? So can we prove it? Can we disprove it? So what the nice thing is that chemistry always gives you some sort of fingerprint, some sort of trigger, of course also a bit of pain. And what we find here also, or what has been shown, is that clouds always amplify these temperature differences. And you see this very nicely here. So here I'm showing you the material composition of what these cloud particles are made of. They are always a mix of materials. And these are a mix of metal oxides and silicon oxides. And you see that the metal oxides and the silicon oxides expand much more into the night side. Oh, sorry. On the evening terminator, so that's much more present than on the morning terminator. On top of this, the particle sizes change, and now the question is, what can we use in order to observational analyze such complex systems? And one of the questions is now, of course, can we use polarimetry, which JWST unfortunately cannot do. To prepare this, bear with me a second, and let's think through what kind of phases we actually can see and what kind of phases may help us to disentangle these asymmetries to learn more about the chemistry. Here we have the star, and here we have our planet moving around it. We are sitting here, we are the observers. This is when the planet is in full transit, and now the planet orbits around. We see more and more, in black we have the night side, in light and in grayish we have the day side. So the planet is moving around, and we begin to see more and more of the day side. At some point the planet disappears behind the star, we don't see it anymore, and then it reappears on the other side. So, and we have just illustrated this here a little bit more clearly to see what of the day and the night side is visible. And here, to change perspective a bit, I have put Cheops as our observatory. Now, the phases where we really can learn the most about the chemistry are these four. So, just beside our planet and just before the planet, beside the star, and just before the planet moves behind the star and when it comes back. And these are these four. And we just have, for a second, we now have to remember these four phases. Because now we can take the next step and find out if polarimetry indeed could be the next step to really explore in much more detail the chemistry, the gas phase chemistry, but in particular the clouds. Because so far it has been extraordinarily difficult to make direct measurements of either the cloud particles, their composition, their shapes, what have you. And in order to understand planetary atmospheres, we really need to get a grasp on these properties. So here we have two values. This is the reflected flux as function of wavelength, and here we have the degree of polarization. In the black line, the solid line, is what we would see from a clear atmosphere, and all the colored lines are what we would see from a cloudy atmosphere. And you immediately see the go-to property is not the reflected flux, but it's the degree of polarization. And the reason is we now can see and distinguish differences. We see here in blue, the degree of the degree of polarization for the morning terminator, and in orange we have it for the evening terminator. So there is a clear difference here in the degree of polarization, such that we can distinguish both. What is more, we can also distinguish if these particles are just spherical symmetric, or if they have a beautiful crystal structure, being some sort of gemstones, which I really would favor. So there is a clear way forward. Now, a little bit out of the JWST area, but I hope we can combine this and really learn a lot more about exoplanetary atmospheres. I would like to come to an end by presenting a summary of the processes that actually are going on, and I really would like to invite the community here to join us in this endeavor, in this multidisciplinary endeavor to understand extrasolar planets, because of course our planets are not only those in our solar system, but they are present throughout the entire galaxy. That means there must be effects of metallicity, there must be changing effects of the external radiation. So I'm really curious to see what we can develop and make of this over the next couple of maybe 5 to 10 years, because I think the area that we are living, or the era that we are living in, is actually those of the characterization of the diversity of extrasolar planets for a galactic planetology. Thank you for your attention.
Thank you very much. Now, questions?
Thank you for the very nice talk. I would like to ask about the graph that you showed with the dip in different wavelengths. And
That one?
no, it's a bit back. Yes, here. So and you said, for example, that we can see signatures of water and other molecules. I don't understand how.
Thank you for this question.
How do we understand this? Yes. Okay. Thanks.
Okay. So, okay, let's first do the simple answer, and then we can go into the depth. So what they basically did is they calculated the individual contribution of the individual absorptions from the individual molecules. And it turns out that if you assume that your atmosphere is made of, actually it's not even an atmosphere, it's a plane parallel slab of gas that you fill with your favorite gas, in this respect H2O, and now you run a radiative transfer and you realize, oh wait a second, this is actually this would be the transit spectrum that I would get. And now I need to add a couple of more molecules in order to really see how much absorption there is. This doesn't really help, right? Let's turn this another way around. Depending on the wavelengths you're looking at, the atmosphere has different sizes because the molecules are located at different heights in the atmosphere, and B, they have different absorption cross-sections. So on the combination of this shows you how deep you can look into the atmosphere. In principle, it is the classical stellar atmosphere problem, if this helps a little bit more to understand this. Just that this is not anymore an atmosphere where the flux is transported from inside outwards, but you are transporting it through the entire upper region of the atmosphere. So therefore, what you are actually, okay, wait a second, yeah, here. We are transporting the photons are transmitting through the entire temperature range that you are seeing here, and you only, and most often we only observe the upper part, and this is why I said it's actually only the top of the iceberg. We only see those gases, those optically thin gases that are present in the upper part of the atmosphere, right?
Yeah, we have one more question.
Hi. I'm Veronica Allen, and I'm in the Kaptein Institute in Groningen, Netherlands. This is really great and really interesting, but I'm an astrochemist to study star-forming regions with ALMA. Can we do this with ALMA? Because we got a lot more molecules.
No.
Why not?
Because they're so incredibly faint. They're at what Madu just told me. We are looking at objects. They are 40 parsecs away. This is really insane. So, but what we can do, and for ALMA, we need. What we can do with ALMA is, for example, studying brown dwarfs. And I must admit, I just excluded this slide here because we can use brown dwarfs as gas giant analogs. And we have done this. So there is one observation of a brown dwarf with ALMA, but it's only a detection. So we couldn't really say how much of that ion was there. So I think if you want to go ALMA, we should really go more towards thinking about the ionized atmosphere, so that we have simply more signal. But this doesn't work for planets. That's really, there's just too little. It's already hard for the solar system.
More questions? I don't see any, so we will proceed with the next point. Let's set. Thanks a lot.
So our next item is now the ANA Prize. So I'd like to call to the stage Arunas Kucinskas, the chairperson of the ANA Board of Directors, and Thierry Forveille, the editor-in-chief of ANA, who will be presenting the 2023 ANA Award for Best PhD Thesis. Let's give them a round of applause.
So it's my pleasure to introduce Raphael Skalidis, currently at Caltech, but who did his PhD at the University of Crete in Heraklion. The ANA Prize for a PhD researcher is for a paper, a first author paper published during the PhD. And in the present case, the paper is about measurements of a method for measuring magnetic fields in the interstellar medium. The magnetic field is an essential ingredient of ISM dynamics, but unfortunately, it's extremely difficult to measure, to the point that ISM astronomers kind of use it as a waiver. When they don't understand something, they say, well, it must be the magnetic field. We can actually measure it, and the method that Raphael developed builds up on a celebrated pair of papers from the 50s by Davies and by Chandrasekhar and Fermi. The principle of the method is to use the polarization of dust as a probe of the magnetic field. And the trick is to use how well the polarization of dust is organized, the morphology of the polarization across the map, as a probe of the balance between the organized large-scale magnetic field and the small-scale disorganized magnetic field. And what was shown in the 50s by Chandrasekhar and Fermi is that the balance of the two, what was shown is that the small-scale disorganized magnetic field is in equipartition with the kinetic energy. And if you put all of that together, you can show that for incompressible turbulence, the magnetic field is proportional to the dispersion of the orientation of the polarization. And that's the CDF method, the DCF method, sorry, Davies, Chandrasekhar, Fermi. What Raphael showed is that, pointed out, is that turbulence in the interstellar medium actually is not incompressible, but very much compressible. And if you take that into account, he showed through very smart analytical work that the magnetic field actually is not proportional to the dispersion of the orientations of polarization, but to its square root. And the paper, which is recognized by the prize, is actually a probe of his analytical work using numerical simulation, MHD, compressible MHD simulations of the ISM. And what he did show is a very important result, is that, yes, taking compressibility into account does make a big difference, and means you can estimate the magnetic field, measure the magnetic field to within a factor of a few, factor of 2 or 3, rather than within, at best, an order of magnitude when you make the incorrect approximation that the field, that the medium is incompressible. And that's, I think, a very important result, and I'm very glad that we're giving the prize for this very important paper.
Thank you very much, Thierry, for a very nice introduction. Good afternoon, everybody. It's a real pleasure for me as the chair of the board of directors of ANDA to present you with this prize, Raphael, because we all, and at ANDA, and I believe all of us here, we are really proud of people like you who are really doing a contribution, important contribution to science. And that's, I think, this is really what we are happy and what we are really proud of. Another thing is that I know that there are more people, more young people in the audience here, PhD students, young career researchers. I would really like to encourage you to actually apply for these prizes. We actually have two. One is for the young career researchers and the other one is the PhD prize. Please do apply for the next year. We are really happy to receive this input from you. And as I said, you know, without you, there is no future, because you are the future of astronomy, and I think I'm not really exaggerating that. So again, congratulations, and thank you very much for your contribution, and I'm really happy to present you with this prize. Congratulations again.
Well, thank you very much, and from my side, I would like to thank the Board of Editors of the Astronomy and Astrophysics Journal for this prize. It's a great recognition, and it supports all young researchers to move forward. Thank you very much.
And to add a last sentence of compliment to what Arunas just said, to apply for the prize, you need to have submitted your papers to ANA. So please submit your papers to ANA.
Very good point. Thank you very much, Thierry and Arunas, and congratulations to Raphael. Thank you. Now we have a very short detour of the scientific program with the gamification extraction of prizes. I know a lot of you have asked about it. We have 4 prizes that they're going to have the extraction now. If the technical staff provides to it, we have the 4th prize will be a publishing book by, a book by ANA and IOP Publishing. The other will be 3 Springer's book. The 2nd prize is a free conference dinner in our next EAS annual meeting. And the first prize, apologies. And the first prize is a registration for the next EAS annual meeting. So, let's see. Yep. Here you go. And the winner is Kaja Malek. I remind the winners that they have to pick up the prize here today. They will not be shipped, so go to the registration desk to pick up your prize. Andreas Peter Joe from Eötvös Loránd University. Congratulations. Irina Chermeriska, Institute of Astrophysics in Paris. And now for the grand prize. Dr. Lukasz Sportak, Ben-Gurion University of the Nevada. Congratulations to all the winners. I remind those who won the prizes, the books, to go pick them up at the registration desk. So now it's time for the closing remarks. We're already there. And giving a few words about it, our president, Roger Davies.
Okay, well, opening and closing, Alpha and Omega, my pleasure to say a few words. What a wonderful week of astronomy we have had here in Krakow. The fantastic image of Rho Ophiuchus to mark the first anniversary of JWST data really underscores, it's a big star-forming region, right? So new starts, the future is unlimited. So we've had a terrific week, inspiring science, lively sessions. The ones I've been in certainly were characterized in that way. There are many people to thank for this, so I'm going to give some thanks first and then say a few remarks. So, of course, first of all, we should thank our Polish hosting committee for putting all this together. And recall that the Polish Astronomical Society is celebrating its 100th anniversary, and here we are in Krakow on the 550th anniversary of the birth of Nicholas Copernicus. I'll return to some of that in a moment. The other people we need to thank are the annual meeting board. That's a combination of the local hosts and the EAS Council. These guys work incredibly hard all through the year. You don't see it, you just see them here in the week. They work very hard here in the week as well, but please give them a big hand. And of course, one of the big successes of the EAS annual meeting is that people who have a smart science idea and wish to get a few people together to bat around ideas about it can organize a session. And the session organizers do a great job, and they are the core, really, of this meeting. And so please thank the session organizers. Thank you to all of you. And then walking around this wonderful exhibition center, conference center, excuse me, you will see as you walk around, there are all kinds of exhibitors and sponsors that help us put this conference on, and they want to show what they can do and what they do in this area. And so let's thank the sponsors and the exhibitors as well. Okay, there's one more thank you to do, but I'm going to leave that to Sara. Okay, so Krakow, it's a special place, isn't it? I mean, we've presumably all had a bit of a chance to walk around and see some of it. There are the Jagiellonian University, founded in 1364. The big church in the town square, St. Mary's, built in the 14th century. It's an ancient place, but it also has a very important place in modern world as well. Some of you were at the reception on Tuesday evening. You will have heard the deputy mayor, I'm going to report what he said, reporting that in a city which has a steady state population of 800,000 people, they are hosting 300,000 Ukrainians. So these people are, of course, fleeing from the war. And so Krakow is doing an absolutely splendid job at supporting those people, and we really are very grateful to be here. We have, of course, distracted them slightly from that role this week, but it's a terrific place. They are a place with a very powerful future. So, thank you. So put yourself in the position of a young person in the 14th century coming to Krakow, never been to Krakow before. Maybe you're coming with your family to sell something at the market or maybe visit a relative. So you approach maybe by the river or maybe on land. And of course, there are really only single-story buildings apart from these huge churches, one or two huge churches, and the buildings of the Jagiellonian University. What's passing through your mind as you approach Krakow? Well, these are pretty awesome sights, right? And then maybe you go into the big church, and there your mind inevitably will turn to the questions of your origins. Where did we come from? Your fate. What's going to happen to us? And of course, these are the very same questions that we are attacking and addressing today in modern astrophysics. They're age-old questions, questions of origins, questions of fate. And we've had some fantastic talks from plenary speakers and in the sessions on exoplanets, on star-forming regions, on our origins, on galaxies and cosmology, black holes, the origin of the chemical elements, our fate. So these are the same age-old questions that we address, that are addressed across the academe. We have our own physical science approach to this, and it's a long-standing series of questions. We are much closer to the answers than we were, but we still have a lot of different aspects to these questions, which we continue to address across a huge range of subjects, particularly in astrophysics. Okay, so I want to come now to sort of the themes I picked up here at this year's meeting. And I think really the strong theme that I've picked up is this is a meeting, a diverse meeting, but one full of young people. The ANA prizes that were just given emphasized the importance of young people to our field. As well, of course, more or less along with that, a meeting that has a lot of young people. About half the people at this meeting are either students or early career researchers. Along with that youth comes diversity, and in particular gender diversity. And that's been very obvious, I think, just looking around. You can see it for yourself. I don't need to present you with statistics. And one of the things, my final comment really is that I want to announce now that the Merak Foundation, they already announced a new prize for the George Lake Innovation Award for people working in many of the sort of unsung heroes of astrophysics, those who develop techniques, new instrumentation and so on. But they've also committed some funding to the EAS to support young people to attend the annual meeting, either through registration waivers or some travel support. So I'd like very much to thank them for their support, and I'd like you to thank them too. So with those few words, I think my part in this closing ceremony is over, and I'll hand back to Sara.
Thank you, Roger, and thank you for this wonderful announcement about the increased support for early career researchers that we will be able to offer thanks to the Merak Foundation. Now, I'd like to call to the stage Kevin Govender and Vanessa McBride, respectively Director and Deputy Director of the IAU Office for Astronomy for Development, and Charles Takalana, who's the head of the Secretariat from the African Astronomical Society. And they have an announcement related to the IAU GA of 2024.
Let's fly the flag. Thank you very much. I must thank the EAS Council, as well as the local hosts here in Poland, for allowing us these few minutes to invite you to Cape Town in 2024, to the International Astronomical Union's General Assembly, the first ever to be held on the African continent. The EAS has always been really supportive of efforts to nurture greater collaborations between our two great continents, and we thank them and recognize their ongoing support. So I'm here with a lot of colleagues, some of them, Dr. Charles Takalana, Dr. Vanessa McBride are my vice chairs, Dr. Sally McFarlane, Dr. Stapile Kolwa, Dr. Daniel Kanama, Dr. Petri Väisänen, Professor Mirjana Povic, lots of them. But on behalf of this crowd, and us on behalf of the astronomy community on the African continent, would like to invite you to Cape Town, 6th to 15th of August 2024. We invite you to come and share your science with people from across the world at the biggest international gathering.
We invite you home. South Africa is normally referred to as the cradle of mankind, and there is no fitting stage for us to come together as the global community of astronomers to come and celebrate our origins as mankind.
We invite you to come and be moved by the spirit and the culture of Africa. We invite you to come and connect with all of us as astronomers in Africa.
We invite you to come and see why we are all children of Nelson Mandela and be inspired by the strength, resilience, and love within us all.
We invite you to come and see African skies, to visit our fauna and flora and some of the biggest telescopes in the world.
We invite you to come and feel the spirit of Africa, to come and know why we are so resilient, why we are a people that are celebrated worldwide culturally.
This will be more than just a conference. It will be an opportunity to change the way the world sees Africa. By showcasing the incredible capacity of our people to build great infrastructure and to do great science, we want you to embrace the opportunity, be our ambassadors in your institutions, in your countries, and bring them all to Cape Town in 2024, along with your families for an adventure that I'm sure will inspire you forever. We will create opportunities for you not only to share your science with a global audience, but also to contribute to society and the environment. Opportunities that will more than balance your carbon footprint in traveling to Cape Town. And there will be ample opportunity to fully engage with subjects you're passionate about, whether it's research, education, outreach, equity, diversity, inclusion, climate change, whatever it is. Friends, the words on the South African coat of arms are Ike, Tara Ike. It means diverse people unite. Let us all unite under the African sky in August 2024, and let us celebrate our diversity, because therein lies our strength as the astronomy community. Our diversity is what will grow not only the field of astronomy, but will grow us as people. Of course, the IUGA will primarily be about growing our minds through the sharing of scientific advancement from all over the world, but its location will ensure that it also grows our hearts. Because scientists are people first. And when we recognize each other as people first, people with families, people with feelings, people with passion and talents beyond their science, when we recognize this and connect with each other, that's when magic happens. That's when creativity shines, and when we inevitably achieve more in exploring the universe together.
South Africa. South Africa. When we are balega, South Africa. When you are balega, South Africa. Shosholoza.
Thank you, Kevin, Vanessa, and Charles, for this wonderful display of what, and a little bit of a teaser of what next year IUGA will be. We very much look forward to visiting you in Cape Town next year. Thank you. And now, we are at the very end, and there is a tradition now at the EAS annual meeting, which is the handing over of the flag. So the committee, the current hosting committee from Krakow, Dorota and Milena will be, Dorota Kozel and Milena Ratajczak, I hope I'm sorry about the names, will be handing over the flag to the new hosting committee, Simone Zaggia and Claudia Mignone from the Padova hosting committee. And while a little video teaser about Padova plays, I hope, on a screen, so you can get a little idea of what you're in for. little bit of the city and also the conference center where we will have the meeting next year. Thanks to Simone and Claudia for taking over this rather daunting task. I know there's a lot of work coming up. Thank you. And now it is on to me to give the final thanks. And I think there are a couple of important thanks that we should be giving. The first one is to the Kwoni people, Laurie Bosson, Frank Grossagenin, Marta Guarch, and Cedric Scholli, who have helped us tremendously over these years, and all the rest of the team, which I'm not mentioning, but I know they're making a lot of efforts to make things run smoothly. And finally, to the volunteers. You're too many, I don't know all of your names, I'm sorry, but I've seen you. You have seen them as well during the meeting in yellow shirts, supporting us, uploading the talks, taking pictures, providing information, going around with the microphones. They've been a tremendous help, but they made sure that everything ran as smoothly as possible. And with this, I'm concluding today's session, and I thank you all for attending, and I look forward to seeing you in Padua, whether in person or remotely, next year. Thank you very much.
Thank you.